Let's get started, everybody. Thank you so very much for coming on a great night, and I think it's going to be a very interesting talk. Of course, I'm giving it, so I'm biased. But so let me start this up behind me. Okay, what I'm going to talk about tonight, well, first of all, let me introduce myself. I'm Erik Ramburg, and I work at Fermilab as a particle physicist. And the topic tonight, of course, is global warming and climate change, more general. It's a great topic, really interesting. You're all here because you know it's interesting. But why is it interesting? Well, there are several reasons. And I'd say the first is it's accessible by everybody. There's a lot of data out there. You just need to look through it and take your time and find it. So any level of people can access the data and analyze it themselves. It's really interesting in that respect. Secondly, of course, is it's consequential, highly consequential. And it's not just us, but it's our children and grandchildren who are going to really reap the consequences of climate change. And so that makes it a very crucial and important subject to study. And third, it's just gorgeous. I love it because it reminds us how beautiful our planet is. This is a modeling system called GEOS-5 put out by NASA, and it simulates the flow of particulate matter in our planet. And you can see the beautiful sweep of sea salts coming off of Antarctica, and the great dust clouds from the Sahara moving across the Atlantic, and the sulfates coming from burning of carbon in China and the Appalachian states. But it gives you an idea of the complexity and beauty of the world, okay? And I'm an ultra-conservative when it comes to the politics of climate change. I want to conserve what we've got, okay? And so my goal here is to tell you how we're changing the environment in contrast to conserving the current conditions. So the lifeblood of physics is questions and coffee. But I'm going to start off with questions, okay? And so there's some key questions that I'll be going over tonight. And that is, what is the greenhouse effect? And how does that work? And then what forces are at play in changing our climate, changing the Earth's temperature? And one key aspect of that is going to be the ice ages. And the ice ages, as it'll turn out, are a very important calibration tool for understanding the climate and its response to changes. And so after going through that, I'll talk about what is the latest data on temperature, and how are the ice sheets and oceans changing with the change in temperature. And then a few predictions in the future. So I should say I'm a particle physicist, not a climatologist, okay? So it doesn't make me an expert in climatology by any means. But I've often talked about this subject to the public. And I do have some experience in outreach to the public on scientific research. But the real people that matter are the professionals like NASA and NOAA and things of that nature. And okay, so here are a few key concepts that I want you to come away with after this talk is over. One is that, well, doesn't work. That's, there, okay, let me try that again. Okay, here are the concepts. There's a big difference between weather and climate, okay? And all along I'm going to point out instances of both, whether it's just a weathering process or true climate change. The second concept, which may be hard for some people to accept, is that the climate is predictable, okay? The Earth's climate is actually predictable. And the two biggest knobs that are involved in the prediction of climate change are the planet's reflectivity, how much light it bounces back into space from the sunlight coming down, and then the amount of carbon dioxide in the atmosphere. And those are the two biggest knobs that control the climate. So it's not a whole litany of 10 or 20 variables that you have to keep track of. Keep track of these two, and you've nailed it for the most part. And finally, a key point is that the global temperatures and the oceans and the melting rates of ice sheets indicate that global warming is not stopped. And that's a very important concept to come away with. All right, so an analogy. So I say climate is predictable. And how can that be? We know that there's huge swings. We can have 60-degree differences in the temperature outside, for gosh sake, you know, in one day. So how can you possibly predict that? Well, you can't, okay? This is an instance where you have to keep track of weather versus climate, okay? And my analogy is the beach. I love going to the beach. And of course, you're sitting here and watching the waves coming in from outside. And you say to yourself, oh, this wave is going to be spectacular. I'm going to ride this wave into shore. And it gets to you and it's 6 inches tall, okay? You can't predict the height of that wave, okay? Likewise, you know, you think this little ripple in the ocean out there is not going to be much, but it inundates you, okay? And the next wave comes in and does something completely different. The motion of those waves is unpredictable. But the average height, the average height of the water, is called the tides. And the tides are quite predictable, okay? And down, you know, the timing of the tides is known, and the height of the average of the sea level is known and is quite predictable. And so very similarly to that, weather acts like waves. You can't predict them, okay? But climate is very steady and slowly changing, and you can predict it, okay? Much like you can predict the tides. And note, the main thing that changes waves is wind, but the main thing that changes the climate, or rather the tide, is the gravitational effects of the moon, okay? And they're completely different processes. And likewise, weather and climate respond to are quite different processes as well. Okay, so let's talk about weather for a little bit, and whether it's climate or weather that's affecting us. We've come out of a very cold time, it seemed like to us, very long period of winter, and it seemed like a very cold year. So was it a cold year? How can you tell? Well, you can take the average. The average says that, in fact, last year, 2013, was one of the hottest years that mankind has ever experienced, okay, or historically experienced. This is wildfires burning out of control in Australia, and they got hammered hard last year, really hard. And so if you put up the average temperature of the planet on a table, you'll see, depending on on how you analyze it, it can be number 4, number 7 I've seen. The point is it's in the top 10 hottest years in the history in recorded history, okay? And I'm talking about going back thousands of years. And how can that be? Well, it's because we're biased. We're biased because we sit in one place, we observe the weather, the huge waves of weather coming in and crashing in around us. We don't have a feeling for the average height of the tides, and we don't have a good feeling for the average climate, okay? People are just not made that way. Now, one thing you'll notice about here, this sure seems funny because all these temperatures are in the 21st century of the top 10 hottest years. That's no coincidence, okay? That comes from an analysis of temperature data going back hundreds of years at least. All of the top 10 are basically in the 21st century. Now here is, in fact, this is December, and you can see what I was saying about the average versus the vicissitudes of weather. You can see here that indeed it was cold, and I'll talk about the polar vortex in just a second. But the rest of the globe is plenty hot, okay? And you've got to include the whole globe if you're going to talk about global warming. And here we are in Batavia, in a cold spot, okay? But don't let that fool you. All right, but what about this dreaded polar vortex? Okay, well, the polar vortex is a circulating wind pattern around the pole that actually bottles up a lot of cold air normally, okay? The issue is not that the polar vortex was created, In fact, it's quite the opposite. This year, the polar vortex was highly disturbed. And what was it disturbed by? It was disturbed by huge masses of warm air coming up from the south. And you can see into Alaska here and around the globe. Big clouds, big masses of warm air were going north, disrupting that wall of vortex that keeps in the cold air, spilling out the cold air down into the south. So it was very hot during January and February, even when it seemed cold here. And Batavia, of course, was moderately cold. And like I say, don't confuse weather and climate. They're two different things. All right, so let's talk about climate. And we're going to start by energy flow. So our energy, of course, comes from the sun. And so the sunlight coming in, for the most part, passes right through the atmosphere. It does not get absorbed by the atmosphere. It does get reflected back, okay? Some portion gets reflected back before it reaches the surface, and I'll talk about that. But mostly it passes through and heats the surface. Now the surface responds, of course, by warming up. And the warmer Earth re-radiates that energy that it's getting in the infrared. Okay, we can't see the infrared, and so we don't, necessarily know this is going on. But of course, your cat does. It sits in front of a radiator all the time, right? And so it knows where radiant heat is coming from. Likewise, that infrared light coming from the warm Earth goes back through the atmosphere, but this time, these wavelengths, they get absorbed by the atmosphere quite a bit, okay? And so that infrared heat is captured by gases in the atmosphere. Those gases re-radiate their heat in all directions, okay? So it's coming up from the ground, it gets absorbed by gases in the atmosphere, and I'll talk about that in just a second. And then it re-radiates that in all directions, some of it downwards, okay? And so this is the essence of the greenhouse effect, is that you have radiant heat that's re-emitted back into towards the surface, heating it up, okay? Now, without these greenhouse gases, it would be we should be thankful for greenhouse gases, because without them, we'd be like the surface of the moon, okay? The moon has an average temperature of about 0 degrees, and so would the Earth's surface if we had no greenhouse gases to hold back that heat, okay? And so it would be 0 degrees without greenhouse gases. But of course, with greenhouse gases that we have, carbon dioxide, water vapor, the Earth's surface is 60 degrees. So it's a nice balmy. We should be very thankful for our greenhouse gases. So let's talk about, and I just wanted to point out that this is a more complete picture of the flow of energy on Earth. And it includes things like being reflected, sunlight being reflected. There's different layers you can actually absorb that light: land, ocean, air. Some of it gets reflected by clouds. This radiant heat also gets absorbed by clouds. And so it's a little more complex than what I was just showing you before, but it's not terribly complex, okay? These kinds of calculations have gone on for a long time. In fact, this is a guy. His name is John Tyndall. He's kind of a hero of mine. He's really a cool scientist. You can kind of gauge what kind of person he was by his portrait here. He was Irish scientist. He actually wanted to have a good time. He was a glaciologist, meaning he would go around and study glaciers. And also, he was very interested in gases in the atmosphere. And he showed that carbon dioxide absorbs this infrared light and re-emits it in all directions. He's the one that proved that. And he did it in a traveling show. He would go out into the public and talk about gases and their radiant properties. And he showed that water and methane are also very, very strong greenhouse gases, okay? They also absorb this infrared light. Let me see if my animation works. Okay, let me just get out of here. Try this again. Nope, it doesn't. Okay, well, this little animation shows that the radiant heat coming in and bending the bonds of the carbon dioxide. And so the kinds of molecules that can absorb infrared light are typically big molecules like this that have 3 or 4 or 5 bonds in them. They can absorb that infrared light, and they bend and shake and then re-emit the light in all directions. And so all 3 of these gases, carbon dioxide, water, and methane, all trap some of this infrared light coming from the surface. Now, in contrast to this happy guy, this guy is Arrhenius. He won a Nobel Prize for actually electrolytes and stuff like that, not related to climate. But he actually was the first to really predict the level of greenhouse warming due to these gases. And he said that any doubling of the percentage of carbon dioxide in the air would raise the temperature by 4 degrees. And 118 years later, that's basically what we still expect, okay? Is the latest International Panel on Climate Change says doubling CO2 will raise the temperature between 2 and 4 degrees. Now, this guy, I should point out, was kind of a this actually picture gives an accurate portrayal of Arrhenius. He became the head of the Nobel Prize Committee, and then he started systematically refusing Nobel Prizes to his enemies and then giving them to his friends. So it was real jerk. Anyway, but his science was right on. Okay. All right. So, if water vapor is a strong greenhouse gas, and it is, it's the strongest, okay, why are we worried about carbon dioxide, okay? Why don't we have a H2O problem instead of a CO2 problem? And why don't we regulating water, okay, in the atmosphere? So why not? Anybody? What happens to water?
It's in balance.
It,
Up and down.
well, dang it. Okay. This is what happens to water, okay? It falls out of the atmosphere, okay? And you can, I love this picture here. I think this is, I don't know, is that a little tree there maybe? But of course, it does it all the time, right? I mean, water does not stay in the atmosphere. It comes out. You know, how long does it take for water to fall out of the atmosphere? Anybody got an idea? Well, it's not a year, but more like a week, right? You know, you can think of a parcel of water coming up out of the ocean, going over the mountains a week later, and it, you know, it falls out, right? And so these processes that take water in the atmosphere, bring it out again. You know, it goes over the desert, changes its composition. But CO2 doesn't have any of those effects. It doesn't condense into precipitation, okay? It stays in the atmosphere. It's well mixed. And it takes hundreds, if not thousands, if not tens of thousands of years to naturally get out of the atmosphere, okay, depending on how you calculate it. So, all right, so any questions so far? So, interrupt me at any time with questions if you don't understand something. That's, like I say, the lifeblood of physics is questions. So, all right, we're going to talk about forcings. What's a forcing? A forcing is something that acts on the climate to change it, okay? And like I said at the beginning, there's not that many of these forces that are acting on the climate, okay? There's a few. And one of the big ones, well, first of all, what is it measured in? It's measured in something called watts per square meter. You don't have to have a deep understanding of this, but it's basically how much power is leaving or entering the system per area, you know, per square meter. And so that's the numbers that people use. For instance, light from the sun is about 340 watts per square meter. Okay, so that's kind of sets the scale for forcings. And so if you disturb something by some small fraction or some fraction of that, then that's a major consequence, okay? That's why we're worried about things that give forcings of 1 or 2 or 3 watts per square meter, because that's kind of a significant effect on the sunlight compared to the sunlight. And looky here, this is forcings as a function of year from the year 1000 to the year 2000. And you can see the dominant feature is these negative forcings or coolings, okay? What are those? Well, as it says here, those are volcanoes, okay? Volcanoes emit particulate matter. You saw that in the beginning when I had that animation going. That was particulate matter in the atmosphere that was reflecting sunlight away. It acts like a shroud. It acts like an umbrella, okay? So volcanic dust cools the planet, okay? But that, just like water, it falls out of the atmosphere as well. Volcanic dust falls out of the atmosphere, okay? It comes down as ash. And so it doesn't stay up. It's not like carbon dioxide that stays in the atmosphere. Carbon dioxide, you can see, is steadily rising as a positive climate force, okay? So this, which just started basically in the last couple hundred years with the Industrial Revolution, is inexorable. It's steady. I'll show a little bit more data in just a second. It's rising. It's a positive force. It's a positive forcing on the climate, okay? It's a warming trend, is this carbon dioxide. These guys, if you add them all up, they do not equal the positive ones. So the dominant force is carbon dioxide, and the negative forcings from dust in the air are being left behind by the inexorable rise of the positive forces. Okay, do you understand? Yeah?
How are those measured, Erik?
So there is basically the strength of volcanoes is reasonably well known in the past. And the carbon dioxide content is I'll talk about measurements of the carbon dioxide content in just a second. One last thing is the sunlight. The sun does have a variable output, but it's very small. Okay, it's mostly a very steady kind of effect on the climate. So it's not sunlight changing. Okay, so this was taken from that GEOS-5 modeling and data assimilation project to map out the particles in the atmosphere. And I just captured one frame here. And you can see that outside of Madagascar, a volcano exploded during this model run. And you can see it has a significant effect on the reflectivity of the atmosphere, just this small volcano, okay? And that's the negative cooling force that we talked about in the last slide. And so volcanoes, you know, if we could just put up a volcano every couple years, then, you know, we would probably cool the planet. But really, there are people who suggest that we imitate volcanoes by putting up sulfates in the atmosphere and just dumping a whole bunch of sulfates in the atmosphere. I personally think it's a bad idea, but there are people who think that.
Erik?
Yeah.
About the previous film.
Sure.
I was just wondering about, like, you know, for example, the country of Chile.
Yeah.
Like, I think it has fairly frequent.
Chile? Yeah, I think so. Mm-hmm.
So, I guess what I'm asking is the time frame of this picture. I mean, is that
Yeah.
1 day? Is that 10 years?
So you saw the animation when I started it up earlier. In fact, let me try and do that right now. The question is, what is the time span of this? And you can see actually over here you'll see the volcano exploding. And so this particulate matter gets distributed, as you can see, into the general atmosphere on the scale of, there's a day, 2 days, 3 days, 4 days, 5 days, at that pace, okay? So, you know, this is, the effect you can see immediately lasts for about a month or so, and then it's well distributed and will stay in the atmosphere for a year or maybe 2. Okay. Now I got to find my, there we go.
I'm guessing that putting sulfates into the atmosphere would be a bad idea because that would probably convert to sulfuric acid.
Yeah, you know, there's just all these negative consequences. Plus, you're not dealing with the real problem by putting all these sulfates in the atmosphere, you know. The fundamental problem still remains, and you'd have to infinitely put, you know, more and more sulfates to counteract any rise in carbon dioxide. So counterbalancing one problem, you know, one environmental difficulty with another environmental difficulty seems to me missing the point, okay? You're supposed to be addressing the problem directly. So it's hard. It's very hard. Everything I'm going to say here tonight says that it's a difficult task ahead of us, but That's what this country is good at, is facing up to difficult tasks. So this just reiterates that particulate matter drops out of the atmosphere. Okay, maybe my, it looks like my, oops, I was going to say it looks like my presentation's working. But this is the famous Keeling curve. This shows you carbon, this is from direct measurements of carbon dioxide in the atmosphere. This guy Keeling decided that he wanted to go to Hawaii and stay there for 30 years. And he got paid for it because he developed a system for measuring carbon dioxide on the slopes of Mauna Loa. And so he immediately saw this beautiful oscillation as the deciduous forests in the northern hemisphere drop their leaves, and then as they get in the spring, new shoots, they draw down CO2 from the atmosphere, okay? And then they emit it in the fall when their leaves decompose, right? And so, so you get this beautiful oscillation. But superimposed on that, he noticed, even in the 60s, this rise due to burning of fossil fuels, okay? And coal, oil, all of the fossil fuels emit carbon dioxide in the atmosphere, okay? And mankind's fossil fuel use is causing it to rise significantly. Now, this is not a small amount, but it's a rather large amount. And I'll talk about parts per million in just a minute. These are measured in parts per million of the atmosphere. But the big story is, where is, this is only about half, if we were going to calculate carbon dioxide in the atmosphere from our industrial processes, this is only about half. Where's the other half going? In the ocean, that's correct. And there it is. On the same scale, these are measurements just recently started of carbon dioxide in the ocean. Okay, that's where the other half is going. It's not quite half, it's like 40% or 60%.
You have to do all this in Hawaii.
Yeah, we have to do this all in Hawaii is the question. Yes, we absolutely have to do it in Hawaii. And so one of the problems here is that when you put carbon dioxide in water, you know, it becomes acidic. It's like Coke can eat out an eggshell, right? Because it's acidic. And so the pH of the ocean is dropping significantly. Okay, I mean, this is going to affect sea creatures somehow. We don't know the magnitude of the effect, but it's going to affect, you know, some creatures who depend on certain pH balance. And finally, let me just say that the rise in carbon dioxide and methane is instantaneous on the geological scale. And so you can see this is what's essentially called the hockey stick diagram. And you can see there's a massive spike here in the present day due to carbon dioxide. Same thing with methane. Methane is in parts per billion of the atmosphere. Carbon dioxide is in hundreds of parts per million, okay? So I was going to do a little experiment here, a little quick experiment. Karen, can you turn on the lights for me? Okay, I was going to tell you, what's this parts per million business? And so I've done a very difficult experiment here, and I've got 2 glasses of water. Maybe I could get a backdrop here. And so I'm going to put in 300 parts per million of my carbon dioxide, okay? So it turns out it's about 2 drops. And so there are many people who say, how can such a small component of the atmosphere, as I say there, 300 parts per million equals 0.0003 of the atmosphere. It should have no effect, right? Well, by that reasoning, 2 drops should have no effect on this water, okay? But of course, we all know that 300, that's about 300 parts per million, has a significant effect, okay? I mean, obviously this comes as no surprise, but it indicates how much of an impact that 100 parts per million can have on an optical system, okay? This is, you know, this is not exactly analogous to carbon dioxide. I'm sorry, sure. Yeah, okay. Now,
drink it.
Well, I will, actually. I need a drink. And so this is is our Earth now. This is Earth with no greenhouse gases, okay? It's cold. It's barren. It's very, very, it's the ice ball Earth. Now what I'm going to do is double the concentration, which mankind is going to do. We're going to double the concentration of carbon dioxide in the atmosphere within, a generation. So that's 1, 2, 3, 4. Okay, now this is 600 parts per million. And so it has a distinct difference, okay? 600 parts per million is distinctly different than 300 parts per million. And so this is our future, and this is our present. So I drink to the future, so. Very good. And you're certainly welcome to come up and drink from the present or the future as you wish. Now, here comes the other interesting aspect of this demonstration, which is by no means that scientific, okay? But how are you going to get that dye out of there, that extra 300 parts per million out of the atmosphere, okay? That's like getting the dye out of this water. It's a tricky thing, okay? It's going to take a lot of activity, of filtration and all that kind of stuff.
I had a question. You said that the rate of dissipation as far as the carbon dioxide leaving the atmosphere, is that variable and dependent on certain things, or is it fairly...
Yeah, I'll talk about that in just a second on why carbon dioxide gets out of the atmosphere. And it's a very interesting, it has to do with weathering of rocks, okay, and how fast that happens. That's the major natural process that draws down carbon dioxide. You would think, oh, well, what about planting trees? Well, this is the entire world's forests changing, dropping all of their leaves and then growing new leaves. And look at what small of a blip it has on the carbon dioxide concentration, okay? This plays a role, plant life plays a role, but it's difficult to overwhelm this incredible carbon dioxide rise with just plants, okay? It's not going to happen probably. It's going to be very, very difficult. Okay. Did you like my experiment? Was that
projected is to double the amount of CO2 in the atmosphere. Is there some prediction of what temperature changes would be related to that?
Yeah, that was our friend, as I said, the Arrhenius. He said, double the concentration and you will get a 4 degrees centigrade rise. That's 8 degrees or 7 degrees Fahrenheit. Mean temperature, So we're going to talk about that in just a little bit as well. Okay, now we're going to talk about the ice ages, which are really cool, okay? This is really neat because it's something that, when you talk about climate, you always want to know. What about these great big swings of temperature that occurred during the ice ages? We don't know what caused those. This is, random processes. Not true, okay? Not true. I will make you understand what the ice ages are in 2 or 3 slides and how they came about. So, this is temperature over now, not thousands of years, tens of millions of years, okay? And so, what is the dominant feature of the temperature of the Earth on the 50 million year time scale? It's cooling down, okay? It's cooling down. So, that's the major trend. There aren't these huge oscillations as the major trend for climate in the last 50 million years, okay? It's steady, slow, cooling down. What caused this? Well, 50 million years ago, the Earth was very hot, okay? There were alligators in, northern Greenland, okay? And so, there was no ice on the planet, okay? But 2 events, and this speaks to your question about the drawing down of carbon dioxide, was probably what caused this cooling of down is that, one, India collided with Eurasia to form the Himalayas. Okay, the Himalayas are relatively recent mountains, 50 million years old. That's not that old, okay? Pretty recent. And it was a major upthrust of mountains. And it turns out that fresh mountain rock absorbs CO2, okay, and forms carbonates, which wash out down to the ocean, okay? That's a way of taking carbon dioxide out of the atmosphere, okay? Another thing, and this has to do with plant life, is there was a monster algae bloom in the North Pole, and that thing was called the azolla. And that looks like it also drew a lot of carbon dioxide out of the atmosphere. And so those two forces caused the planet to cool. And enough so that ice could form at the poles, okay, which is not a usual condition in the Earth, okay. Now the crazy thing is, near the end, or near our own time here, let me say this. The change in CO2 during this whole process was 1 part per million every 10,000 years. Okay, that's the scale you have to think about. Now we're putting 1 part per million of, you saw it right here, 1 part per million every 8 months. Okay, every 8 months, that's what we're doing. Okay, so, you know, compared to the weathering processes that the Earth has known, this is instantaneous. All right, so we're going to talk about this, guys. Look at those oscillations. Okay, what are those? Come on. The ice ages, right? Okay. So, this is one of the dominant climatological effects in recent history, is the ice ages, okay? This is our lovely world we have now, and this is what it would be like during ice age, okay? And so, of course, drawing all of that water out and forming ice causes the sea level to drop, okay? And you get these great big land bridges like here in Indonesia or up here in the Bering Strait, which is how 15,000 years ago humans went across into North America. I don't know how they survived. You know, it was pretty tough conditions. This planet probably cannot support, you know, 8 billion people, okay? So, I mean, it's just, there's too much cold weather and ice to support that many people. But, you know, I don't know that for a fact. But the point is that it's a major glaciation. Now, what caused that?
The albedo a lot higher?
Yes, very good. The question is, was the albedo or the reflectivity much higher? You predicted my next comment here, which is that two important changes that cause the acceleration of freezing, of ice sheets forming, is this reflectivity of the ice sheets, okay? And from this new ice. It's reflecting more light back into the atmosphere and cooling us down, okay? It's like putting an umbrella up, or, you know, putting a mirror up, and it reflects all this light. The second thing is that the cooling ocean absorbs more carbon dioxide and freezes things. That's the same thing that was causing, you know, this slow temperature fall is less CO2. Same thing here. You have more CO2 in the oceans. Now, what triggers those things? You got to trigger it. Well, I'm not going to go into too much detail in this. I think it's too you know, the physics is pretty complex, really. But suffice it to say that the Earth spins like a top, and when it goes around the sun, it changes its orientation every 20,000 years or so, and that changes the heat balance on the planet and triggers an ice age. Okay, and those are called Milankovitch cycles, and they're very, as I say, they're very complex, related to the elliptical orbit of the sun, all this kind of stuff. But my point here is that the oscillations creating ice sheets only happen when the Earth is cold. The Earth is cold, comparatively. So here is the real money figure to take from this lecture, I think, okay? And that is, the climate is predictable. Two numbers went into the prediction for temperatures during the ice ages. One is, as I said many times, CO2. The other is reflectivity of the sun, okay, on the ice sheets. Those two numbers gave a prediction, a calculated temperature of the blue curve here, and the red one is measurements from deep cores in the ocean, okay? We can predict the ice ages. We know exactly why they occurred. We know the trigger mechanism. We know what caused them to amplify their ice sheets growing and melting away. And we got the timing down just right. Now look at this. As I say, we understand these bumps that last 800,000 years. From this data, we know now that if we increase the temperature of the Earth by about 3 degrees C, which will happen, we are going to shut off the ice ages forever, okay? That's this little arrow here, okay? You would think that how can we do such an incredible, dramatic change in the climate with such a small amount of forcing? But it doesn't take much. This arrow is about 3 degrees C higher than what we, than where we were 100 years ago. And you see it's higher than everything on this graph, okay? And if as I said, it's just amazing to think about that we have shut off the ice ages, okay? We've done it. Good job, guys. Very good. Should be very happy about that, okay? The ice ages are very difficult to live in. Well, the problem, of course, is when you turn up the thermostat, right, and you let the kids get into that business, then they turn the thermostat up to 90 or something like that. And so we may not stop here. We may stop way up here, okay? And so if we do that, we're going to start climbing up that temperature curve back into the Eocene era, okay? Now, I'm not here to tell you that that's a bad thing or a good thing. I do not know, okay? Frankly, I just don't know. It could be a great thing. Like I said, the ice ages are difficult to live with. And so this is just to say that the amount of forcing from the ice sheets and the carbon dioxide are about equal in the ice ages. And this implies that there will be a 3/4 of a degree change in temperature for every watt per square meter that we put of forcing. So my point about this is you don't have to pay attention to all the numbers here, but it is well understood, the ice ages are well understood, and their effects are very well understood. All right, so let's get into Earth's current surface temperature. So we do not lack for data on terms of the Earth's temperature, okay? Every little village in the US has a temperature sensor, right? Look at them all. And likewise in Europe. And so we have 7,000 temperature stations in the world, all linked together in a database. We're taking the temperature of the Earth pretty well. And so, in fact, you only need about 200 temperature stations, evenly distributed around the world to get a good global average, okay? So don't think that, there's a lot of uncertainty about the temperature at any place on the planet. There isn't. And so this is the latest reconstruction. As I call this the best temperature reconstruction. I don't call it that. It's Richard Mueller that calls it that because he works at Berkeley, and so it's Berkeley Earth surface temperature. But I think he really means it's the best, temperature reconstruction. He actually came in as a skeptic that that the temperature record had any regularity to it at all. It was all broken and needed to be fixed. He soon found out after several years of work that in fact the temperature record is very good, very well understood, and these are the effects of volcanoes, by the way, guys. These spikes, and this is the kind of the prediction, or a fit rather, including volcanic activity. But you can see this is probably I really do believe it is the best reconstruction, because he found a method for stitching together all of those stations, all 7,000 of those stations together. That was a big improvement. And you can see we're rising in temperature. Forget about the absolute value of this number. Just note that it's about a degree or a degree and a half compared to industrial times. Yeah?
These are just sort of normal volcanic activities, right? I mean,
Yeah.
we're not talking about
We're not talking super volcanoes. I don't think so.
That's what I mean.
This one looks big. Does anybody know what that is? Krakatoa? Okay, anyway, there are a lot of people more knowledgeable about volcanoes than me. And so, but you can see their effect. As I said many, many times, the dust eventually falls out and you go back to the curve that you were on, the inexorable rise. You wait for the next volcano and yay, it's cool again, but I'm sorry, the volcanic dust falls out.
But don't you think that like once every certain million years, 100,000
Yeah, once every million years, is there a super volcano?
all that out the window?
Well, the rate of fallout of ash doesn't matter, The answer to your question is yes, a supervolcano would cool down the Earth quite a bit. And so there's no way to predict when that's going to happen or control it. So it's probably not a good idea to rely. Yeah, you know, you have a really long viewpoint. I love that, the million-year time scale. I can hardly figure out what I'm doing tomorrow. So,
So that when the temperature goes down, the CO2 goes down. Is that because?
so actually, no. Think of it the other way around. We're increasing temperature here. What's going to happen to the CO2 in the ocean? It's going to come out probably more than it's going to go in because it's heating up. Okay, a hot cola. A hot Coke is stale because all the carbon dioxide has come out of it, you know.
So the CO2 is not causing these temperature things.
The CO2 in the atmosphere is indeed causing this temperature rise.
It's not the, is it the CO2 from the volcano?
No, the CO2 is coming from our fossil fuel burning.
No, I'm talking about those little.
Oh, the
little,
spikes.
The spikes.
The negative ones, those are volcanoes, yeah.
Yes, and what causes the CO2 to change when the volcanoes go?
Oh, no, I'm sorry, I misunderstood. I didn't answer your question correctly, which is why is the temperature changing during those spikes? It's the particulate matter that it throws up into the air, the ash and the sulfates that come out of the volcano that form that white cloud that I showed you in the animation. And so that reflects sunlight away and causes cooling down.
The red curve is just based on CO2. Oh,
No, it includes volcanic activity.
Okay, I'm sorry.
So this is pretty cool. This is using those temperature stations. Dang it. Okay, this is over the last couple hundred years, 1890s, 1900s. Blue is about -2 degrees. Dark red is +2 degrees. 1913, 1917, 18. This looks pretty good, okay? The globe looks on average, oh, maybe it's a little warmer here, okay. 1940s, we're beginning to feel that it's pretty hot. It did cool down in the 50s and 60s in some parts, the global average. But once you hit the 70s, it's taken off tremendously, okay? And you'll see that occurring here. And that's 2000, and this is 2012. This is not a model, this is real data, guys, okay? So you can see that's a very powerful indictment of, global warming, or anthropogenic global warming is the cause of this temperature rise, I think. It all fits together very, very well. The increase, to give you an idea, the increase of heat into the atmosphere is equivalent to 10 nuclear bombs going off every second, okay? Every second. So let's try and do that. Every one of those is a nuclear bomb coming off, okay? That's how much heat is being trapped by this additional greenhouse gases that we're putting into the atmosphere, okay? Boom, 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 okay? That's how many atomic bombs are going off equivalently. So that's the amount of heat that we have to deal with. So what's happening to all that heat? Well, let's talk about the oceans and the ice, okay? This is a really good story. First of all, the ocean. Once again, you don't have to worry about measurements. We got plenty of measurements by these guys here. These are the buoys, the Argo buoys. And it's an international effort. And you can see there's like 3,000 of them floating around the oceans. They're really cool because they dive down to about 1,000 meters, take some measurements, figure out where they're going. They dive down to 2,000 meters, and then they come right back up and measuring salinity and temperatures all along the way, okay? Really cool little devices. I didn't even know about them until a few years ago. And this is what the oceans look like. No surprise, they are also going up in temperature, okay? They're a little smoother. And, the heat content of the ocean smooths things out. And so, but as you can see, it's the same story. The heat content in the ocean is rising. And this is 2012, 2013. So this is, as I say here, this is the effect of all those atomic bombs going off. Not only warming the atmosphere, warming the ocean as well. Okay? Now, what about the ice? Well, you probably have heard this story, but it's always great to watch. This This is interesting. We're going into a big melt, as I'll show in just a minute. But here's the key thing that I want you to come away with when you talk about ice with anybody, okay? And that is, don't worry about the surface area of the ice, okay? That just tells you, that doesn't tell you how much ice there is. It could be really thin, right? It could be really thin or it could be really thick. You got to talk about the volume of ice. Nobody says, give me 5 square inches of ice in my glass, okay? You say, fill it half full. You know, you get a volume. And so pay attention to volume, not area. Most of the melting is below the surface for floating ice, okay? Or even for the ice sheets on land, okay? You can't see the melting that's going on underneath. This is the curve of ice volume on the planet Earth. This is the Arctic, rather, I'm sorry, not the combined one. This is the Arctic ice volume as calculated by a group called Biomass. And you can see this is not zero suppressed. There's zero. There's where we started. And we're darn close to zero. How can that be? We can't be that close to zero, can we? Well, yes we can be, because I just can't. There we go. Okay, so this is the ice area. I told you not to worry about this ice area, but it's still interesting to watch. This is 1989. You can see this is the Northwest Passage. This is the Northeast Passage. Most of them are blocked. This is the warmest September month in the Arctic. But starting around 2000, you can see both the Northeast Channel and the Northwest Channels are opening up and free of ice. 2009. Now you can like take a rowboat around the northern. So this is the area of ice in 2012. You can see you can now circumnavigate the poles without any trouble, without any icebreakers. That's certainly the first time in history that you can make that statement, I think. But the mass, this looks bad. It looks like it's shrunk by about a half or something in terms of the area. But forget about the area. The mass is down by a factor of almost 5, okay? So we got 20% of the ice volume in the Arctic left. And I'm telling you, it's just going to go away, okay? I mean, whether this flattens out, it'll never really tick up major, okay? It's just going to flatten out, and within about, within 10 years, essentially most of the, some people say, oh no, it's going to take 20, 30, 40 years. I think it's going to happen in 10 years just from looking at that graph, That's, nobody really knows. Nobody really knows. But it's not 100 years. It's not 200 years. It's right around the corner. And so what about the great ice sheets on land? Well, this is very instructive as well. GRACE is a pair of orbiting satellites that NASA runs that go in a circumpolar orbit, and they measure the gravity underneath them by how these things move. And so we're going to look at Greenland now, and this is the year 2004. This tells you the thickness of the ice sheets, basically the volume, as I was saying, okay? And so let me just stop. Ah, darn, sorry. I am just having troubles with my computer here. So let's do that again. The story is that Greenland is also melting, okay? And you'll see how it's melting, which is really quite fascinating. It's melting from the southern, but also from the northern regions simultaneously. So here you can see 2004 and 2006. This is 0 centimeters. This is 120 centimeters. And so you can see that already in the southern tip, that's 2009, 2011, and 2012 up there. So you can see, more than a meter of ice has melted. That's a lot of ice for the size of Greenland, okay? I mean, that's a lot of ice. So it has a ways to go. We're not going to melt Greenland in 30 years. We are going to melt the Arctic floating ice cap, but not Greenland. Greenland's got a lot of water in it, okay? So, okay. Let me just point out that Antarctica, when you measure the mass using these GRACE satellites, you also see the exact same behavior, okay? Again, don't let anybody tell you that the ice is growing in Antarctica, because they're going to be talking about area, okay? Talk about volume. Always bring the subject to volume. Amount of ice, not square inches of ice, okay? And you can see it has the same behavior as Greenland. The loss of mass in all the ice sheets is about the same as you'd expect. They're all going down together. They're all accelerating their degradation, okay? And what's happening to the sea? Well, as you can imagine, some of that water, a lot of that water goes into the ocean, okay? All of it, essentially. Now, that's not such a big deal for the Arctic ice cap because it's floating already, okay? You're not going to raise the sea level by the Arctic ice caps melting, but you are going to raise it from Greenland and Antarctica. And you can see this is the sea level. Sea level is indeed rising, and it is indeed accelerating, okay? Just like scientists predicted, you know, a few years ago, 10 years ago. So, frankly, I don't think anybody really knows how fast this will accelerate. We're not really for sure.
Erik,
Yeah.
does this have an impact on fresh water versus salt water?
Well, it all goes into the ocean. All the major, the question is does this affect, you know, for the freshwater stores and everything? All of the water eventually is going to make its way to the ocean from Greenland and from Antarctica and from the Arctic ice cap. All that just flows directly into the ocean. So.
Will increase rainfall.
Well, it's not so clear. We'll talk about drought in just a second. And we're winding up, we're coming to a close here. But let me just say that if you plot a very simple extrapolation, this is not a real scientific fit because the behavior is a little more complicated than this. But it does give you the scale of water level, sea level. This is measured in meters compared to temperature change. If we raise the temperature by 3 degrees, can we really be talking about 50 meters of sea level rise? Well, yeah, we can be talking about it. It's probably not that much. It's probably only 20 if you do a careful analysis. 20 meters, 60 feet. Okay? So the order of magnitude for sea level rise for our equilibrium temperature is about 20 meters. Okay, and this is what happens if we get a meter of sea level rise. The Everglades are gone, okay? That's too bad, I really like them. Miami's gone, I lived there once. That's not such a big loss, but... Now 20 meters, you're talking about the whole state of Florida, okay? So now we're talking Houston's gone, and New Orleans, and all of Florida, and most of the seaboard of the Atlantic, and certainly down here in Mexico, the Yucatan as well. So now this isn't going to happen in your lifetime. We don't need to get all in a panic about it. It's going to take, what, 200 years or 500 years, something on that order, okay? But don't get into the notion that this isn't going to happen. It's all a fantasy. It's not a fantasy. It's, you know, basic, fundamental data analysis, okay? And so it very likely will happen, but we can talk about it and reason it out, okay? That's what we do. That's what humans like to do. So this is the last part of my talk here, facing the future. We don't know what's going to happen, okay? Why do we not know what's going to happen? Because we don't know how much emissions that humankind are going to put into the atmosphere. As I said, CO2 is the major driver of climate. If you put in a lot of CO2 compared to where we're at, let's say up to the year 2100, then it's going to be hot. These are very hot temperatures, up into the 10 degrees. It's insane temperatures up here. If we flatten out our CO2, it's going to still be very, very hot, but maybe more survivable. If we actually reduce our emissions dramatically, we could maybe escape the worst. I doubt this will happen. I'm not so clear whether this. I don't doubt this. It's certainly a possibility. Okay, I don't know. These are from models. Okay, and these are not data. We're extrapolating into the future. So let's talk about the future really quick. Whoops, sorry. This asks the question about fresh water. It's more likely that there will be drought conditions rather than a lot of fresh water. I mean, there is flooding, but this analysis from Day in 2011 indicates that Some regions will have a nice freshwater flux, have plenty of rain. Other regions will likely, especially the Mediterranean, look here. This is something very worrisome. You know, the countries of the Mediterranean may really be hurting in terms of drought in the future. But again, this is a model. This is not data analysis. But we have to be clear in our heads that this is not a fantasy. You know, this has very likely, parts of this are likely to happen. Now, what's the problem? Look, this is very near the end of my talk. And I want to point out to you some very important aspects of our carbon dioxide emissions as a species. So this is some of the major countries in the world. This is the amount of CO2 we emit per person, and this is the amount of wealth per person we have. Okay? Notice this country way out there. Who is that? That's us, US. Okay? This is 1965, by the way. We have a lot of CO2 emissions. We have a lot of wealth. Okay? And there's about a linear relationship between the two. Okay? Except, look at this. When we look 2006, or 2011, I'm sorry. What's happened? Well, we've doubled our, our CO2 emissions, and we've gotten more wealthy. But look at what Europe did. They increased their wealth without adding CO2 per person. Okay, this is the same location of these European countries in terms of their carbon dioxide emissions per person. See, that's them here. Okay. Without changing the amount of CO2 per person, they've somehow figured out how to have a pretty wealthy society, okay? We need to emulate that, okay? We need to bring this guy, us, over to here, okay? We'll still be wealthy, but we'll be emitting less carbon dioxide, okay? It's not impossible. It's doable. Japan, Japan is in here as well. Japan and Europe have shown the way. It's not hard. It's doable. Now, this is the amount of CO2 that we emit in our country. And even though we're gaining population, in 2012, we emitted less CO2, absolute terms, than we did back here in 1992. That's a good start, okay? Why? Mostly because of the rise of natural gas. Natural gas emits much less carbon per megawatt hour than coal does, or oil, okay? The amount of emissions of carbon from natural gas is the lowest among the fossil fuels, okay? And we're doing the right thing by switching over to a natural gas economy, okay? But we need to go further. But we should take the carbon, or we should take the coal out of the equation, okay? It's really bad. So this is my summary. Climate on Earth is predictable. There's two knobs that control climate. One is CO2. The other is, as I said, reflectivity, like the volcanic aerosols, okay? The water vapor in the atmosphere just follows along for the free ride. It doesn't really lead the way. Carbon dioxide leads the way. Man-made CO2 emissions is the dominant climate force, and it's predicted to lead somewhere between 2 to 4 degrees centigrade, okay? And temperature measurements are very clear that it's not stopping, it's continuing, and that the greenhouse effect is still there. And all the major ice sheets are dramatically decreasing in mass. And my final point is change is possible. Let me show you somebody who changed things. This is Jim Hansen, the head of the climate modeling group for NASA, okay? The greatest climate scientist in the world. And he quit recently to be an advocate because he says, my grandchildren are going to face a difficult planet. I want to fix this, okay? He's being led away in handcuffs, okay? I mean, this is a crazy kind of consequence of this. But, I mean, this man should be showered with praise. He was warning about this in the 1980s in a very realistic manner, okay? And so let's see what he says. Every major national science academy in the world has reported that global warming is real, caused mostly by humans, and requires urgent action. The cost of acting goes far higher the longer we wait. We can't wait any longer to avoid the worst and be judged immoral by coming generations, okay? That's the standard that Yeah.
Why was he arrested for speaking out?
Protesting, this could be the pipeline, I think, is when he was protesting that.
Okay.
You know, because the tar sands in Canada are almost as bad as coal in terms of environmental problems. So what kind of change can you do? I'm not here to harangue you about making changes in your life that are, you know, stop doing this, do this instead. But I am going to tell you to do one thing, okay? And that is a very courageous thing that you can do, and that's vote, okay? Your voice gets amplified tremendously when you vote on these kinds of issues, okay? It's the best thing you can do. You know, replacing your light bulbs is not going to change much. But replacing every light bulb in all of the federal agencies in the country will do something, okay? And the only way that you can ensure that that kind of positive thinking is by voting, okay? So anyway, thanks a lot. And you can always talk to me or email me. And I'm going to put these slides on in my Dropbox, so it should be available if you want. Anyway, thanks, guys. Yeah.
The disappearance of Miami and then Florida, was that modeling or data?
Yeah, the question was the disappearance of Florida and Miami. That is definitely modeling, okay? But, well, no, a better way of saying it is, no, that's not a true statement. That is just geography, okay? So that is just factual. If you had a 1 meter rise of water, that's what it would look like, okay? Or if you had 20 meters of water, Florida is gone. That's just a fact. But the question is, how much will the sea level really rise? That's modeling because it's in the future. We don't know, and it depends on the emissions of, you know, fossil fuels. So, you know, the way to say it is, we don't know whether Florida is going to be affected like that in the future because we just don't know how much emissions we're going to pump into the atmosphere. And so it's very clear that carbon dioxide is the culprit, though. And so it all depends on that.
As CO2 concentrations go up, I know plant growth
Yeah.
goes more rapidly too. Won't that have some mitigating effect of turning slope down?
The question is about CO2 goes up and you get plant life improvements. Even if that was the case, I am not an expert on that. I showed you the curve, the Keeling curve of the rise of carbon dioxide and the little oscillations in it, right? Those little oscillations are the entire forests of North America, of the northern hemisphere, fell off and emitted their carbon dioxide, or they grew, you know, a whole new component of leaves in the spring. So those little tiny oscillations are the effect of the entire forest systems of the northern hemisphere. So my point is, yes, CO2 will have an effect, but it can't compete against the rise of CO2.
With extra algae growth and the hydrogen sort of as a trigger, and
so the algae growth.
by itself, if it was taken isolated, I see you see small oscillation, but it could leverage.
Yeah, I mean, it could help. There's conceivably genetic engineering you can do on trees or something that make them super CO2 absorbers or something like that. I'm just saying that just from an initial look at that Keeling curve, it seems to me very difficult to compete against the natural processes of spring and fall, you know. And I don't think we'll ever match those. And algae blooms aren't going to happen for a while in the Arctic like they did a long time ago.
But the burning of the Amazon forest
Mm-hmm.
and the clearing of so much of our trees in the Northwest, how do they factor in?
So yeah, the burning of trees and clearing of forests, I actually don't know. I'm not an expert on much of this stuff, but again, my impression is that yes, those contribute to the problem, but the dominant problem is carbon dioxide from fossil fuels, okay? Now, the thing about forests, of course, is if you grow a forest and cut it down, burn the carbon, and grow it again, that's neutral in terms of the carbon dioxide content it gives to the atmosphere, because a growing tree takes carbon dioxide out of the atmosphere. You cut it down, you burn it, you put carbon dioxide back in the atmosphere. That's why biofuels are a potential solution, better than any kind of fossil fuel solutions like natural gas. So yeah, we should be turning to biofuels as much as we can, and of course Obama has done that in the Department of Energy. Yeah.
I've heard a lot of negatives about the production of natural gas, leaking of methane.
Yeah.
Environmental
Yep.
destruction.
Yeah, the leaking of methane from natural gas wells is a big problem, and it's probably underestimated. It's probably underestimated. So I've been doing some reading on methane, and it's not clear at this moment whether that'll be a significant contributor. Right now, there's no question the carbon dioxide content is, but that's because it's at 300 parts per million, or 400 now. The methane is in parts per billion, so 1,000 times lower, basically, or hundreds of times lower. It's a pretty effective greenhouse gas, more so than carbon dioxide, but it hasn't reached that level, where it's a worry. Now, vast sheets of unknown organic matter start going thawing in the tundra of Russia. It could be that releases a lot of methane. Don't know. It's a scary scenario. Yeah.
Can we go back for a second to how greenhouse gases actually work? How do they store and reflect the energy?
Right. If I can get my darn animation to work, I had troubles all during the talk here. Oop. Here's my... Okay. Here's my favorite. I love this guy, John Tyndall. He's really great. Yeah, it still doesn't work. Dang. Okay, I can just tell you though. So the molecular bonds in a triatomic molecule like CO2 has got 3 atoms in it. H2O has 3 atoms in it. CH4 has 5 atoms in it, okay? All of those molecules, when infrared light hits them, they bend. Those 3 bonds can bend, okay, and oscillate and stuff like that. That's basically, they're absorbing infrared. Now when they slow down, basically, they emit infrared again, the same light, okay, that caused them to bounce in the first place. There's no energy lost. It's just redirected because there's an upwelling of infrared light from the surface of the Earth. It gets captured by these carbon dioxide or greenhouse gases. They bend and shake, and then they re-emit in all directions, okay? Some of it downward, so some of it back to where it came from. And so you're trapping some fraction, basically half, of the infrared coming from the surface of the Earth. Now, that's not true for nitrogen or oxygen, the dominant components of our atmosphere, because those only have 2 atoms, and their bonds are very strong. They're not shaky like CO2 or CH4. Somebody else over here? Yeah.
I'm sorry I missed the very first part of that.
Okay.
But as far as solar output changing over time,
Yeah.
does that relate to?
Let me see if I've got that here, right here. So you can't really see those oscillations. It might be hard for you to see them. Just a minute. Right here is the best place to see the oscillations of the solar effect. I don't know if you can see the little bumps kind of going there. Yeah, those are the oscillations of the solar output. So it's not very much. Okay. It's, in terms of numbers, it's 0.2 watts per square meter, something like that. Whereas CO2 is 1.5 to 2 to 3 watts per square meter eventually. So it dominates by an order of magnitude.
60 million years ago, how much greater was it, or was it?
Well, I don't think we have a year-by-year count of what it was like in ancient.
I guess I'm just looking for over a very long period of time.
Yeah, the sun does change its intensity over these tens of millions of years, and that plays a big role if you aren't dominated by carbon dioxide. So yeah, if you take carbon dioxide out of the equation, then sunlight does make these changes. It triggers the ice ages. Okay, so big changes can be triggered by the sun if you don't overwhelm the system with carbon dioxide, which is what we're doing. Okay, so we're just saturating. Yeah.
Okay, so you have the what you're speaking on is true.
Mm-hmm.
So how do you correct it? And when the population is growing and the population
Mm-hmm.
is being blamed for it,
Yes.
population is growing.
Right.
And you have also like the United Nations, that's kind of like a dominant world seer overviewer of things.
I wish I don't think the United Nations is a dominant force, really, but
They seem to have a
people have to accept this story before they're going to ask for changes. And so, you know, I'm doing a very small piece of that by talking about it.
Do you see anybody giving like corrective measures for
Well,
the future for it, or is it just still?
Believe it or not, China is the worst. I forgot to mention this on this thing. I talked about the future of the carbon dioxide emissions in the future. This guy here. The big red thing is China, okay? And so it is the worst emitter of carbon dioxide now. Okay, I think they've surpassed the U.S. Per person, it's much lower, right? Because they have a lot more people, okay? And so they are, however, they understand that global warming is a real problem and they need to address it. I've been to China a couple of times in the last couple of years. You know, it's a severe pollution problems. And they are building more wind generators and more solar generators than anybody else as well, okay? But they can't seem to stop their coal burning, and that's the big problem. Coal is by a factor of 2 the worst emitters. Yeah.
This is similar to what she was asking you with the report that just came out with the international scientists saying you have to get CO2 under control.
Yeah.
And there have been a couple of articles similar to what you're saying, though, that countries like China and India, with their growing middle classes, tend to be the ones that really need to do something.
Yeah.
They're not willing or being as aggressive as they should. And it's kind of what you just did.
Yeah, but who's supposed to be leading the way here? Them? What are we doing? We're supposed to be leading the way, okay? We are the USA, damn it, and let's act like it, okay? Let's act like we're the United States of America. You know, we got this rich history of facing intractable problems and fighting, and you know, it's not for lack of you know, discussion in the U.S. You know, we finally just got to face the facts and do something. And if we lead the way, things will change.
Are you able to predict or have there been predictions made that if tomorrow man-made CO2 emissions went away, dropped to 0,
yeah,
how long would it take until our planet returned to some state of normalcy?
Well, you know, all states of the planet are normal, okay? The question is, how long would it take to return to normal if carbon dioxide emissions happen? You know, all states of the world are normal in some sense. The question is, do we want, you know, to live in that world, or can we live in that world? But the answer to your question is, if we stopped emissions, we still have like somewhere between 0.5 and 1 degree locked into the system already, basically, okay? And so we would still see a rise of, let's say, 1 degree centigrade, but not 4, you know. So we would see the difference within 100 years, I think. But to get back to normal, meaning pre-industrial times.
I mean healthy, right?
Yeah. Well, you know, that's, if we wanted to get back to a pre-industrial times, that would be 10,000 years. Okay. So, you know, we're going to live with this. You know, we shouldn't be. We got to face the facts here. You know, that carbon dioxide, just like that dye, is not going to come out. Okay. It's in there. It's up there, and.
Unless we figure out a way.
Well, if we can figure out a way to get it out, of course, you know, trees. We talked about vegetation absorbing the carbon dioxide. I'll go pour that into our plants at home and see what happens. But I just don't think it's going to be enough, because we've seen what, as I said, over and over again on that Keeling curve, what the effect of the entire northern hemisphere's forests is in terms of, you know, changing over its leaves. That's an incredible thing to be able to emulate, you know. I don't think we're going to get there. But I don't want to be, you know, I don't want to put a damper on any possible solutions. We should be investigating anything. Yeah.
So how do we convince the top 1% richest people in this country, the ones who lobby government the most, that it's also in their best interest keep this in check?
Sure. How do we combat the kind of the inequality of voices in our political system? That's what you're really asking. If you think this is a problem, join with others, vote. You know, elect. You would be astonished. You hear cases about you go to a congressman and ask them to solve some problem which seems intractable. Next week it's gone. You know, and it's amazing. It's a democratic society we live in. I know money seems to be overwhelming it, but it is responsive to votes. You know, we know that. And so my feeling is you just have to engender change in politics. And that's the thing you can do from the ground up. Like I said, changing your light bulbs is not going to do it, okay? It's fun to do, and I'm doing it in my house. I don't want to pay that much, you know, I want to pay less money, have more efficient lighting, and contribute what little minor detail I can to the carbon dioxide. But it's not going to solve any major problems until you get somebody at the top. The election of Obama, whether you're a Democrat or a Republican, clearly has made a difference in the attitude of the government addressing this problem, okay? It's no slight on any politician, it's simply a fact. And so take that facts into account when you vote if you think this is a problem, okay? And of course, there's many other issues you vote on, but it's up to you guys to figure out whether this is one of the most important issues or not. For me, it's one of the most important issues. It's what I vote. You know, I vote based on politicians' policy towards climate.